Okay, well, I think I'm going to take a synthetic, analytic approach to this. I'm going to start by drawing in a circle, um, and I'm just going to put it on the coordinate plane just because it's an easy way for me to organize my thoughts about this particular problem. So I'll draw the circle in. I'll center the circle at the origin. Seems easy enough to do. And then start thinking about what we know and what we don't know about this circle. We're told O is the center of the circle, so O is at 0, 0. We're told Q is a radius, OQ is a radius, and that the radius of the circle is 10. So if Q is on the circle, then it's got to have an x coordinate of 10 and a y coordinate of 0. We're told this point P, OP is 6 units, so that's got to be at 6, 0. Well, if Q is here, then I could call this point Q prime. And we're talking about chords that pass through P. So these are lines that pass through P and touch the circle, right? That's what a chord is. And we're told to include the diameter. And if you're sort of looking at that, you have to ask yourself, well, you know, are all of those different in length? And of course they are, right? You can just see that things seem to be growing, growing, growing till we get to there, and then shrinking, shrinking, shrinking in length until we get to sort of what appears to be the shortest length, and the shortest length appears to be that the I guess the chord that's perpendicular to the radius that passes through P. So it seems like that's an important spot to analyze. So I'm going to go ahead and draw that in our picture. And then the question is well, what's that chord length? What's that chord length? And what can be in between them? It seems like that's what we've been asked to do. So let's first observe observations. Well, number one, it appears that Q prime is the longest chord through P, and its length Q prime, let's see if that's 10, 0, and then Q prime has got to be negative 10, 0. So negative 10 to positive 10, so that's got to be a distance of 20. And then the question is, well, how short is that? And is it even an integer length? So let's give that a name. I don't know, PQ, let's call this R, I don't know, R prime. And we've decided that that's where this is perpendicular, so we should be able to get something out of this from Pythagoras, right? So if I take a look at this little triangle right here, OP is a distance 6, right? And we want to know what RP is. If we can double that to get R prime. But we know this is a circle, so it's a collection of points that are fixed distance from the origin, and that fixed distance is 10, so that's a 10, which means that this triangle right here is a scaled up 3, 4, 5 triangle. I can tell that because 10 squared minus 6 squared is going to be 8 squared, so that makes this side 8. So a quick application of Pythagoras there. 3, 4, 5 times 2 scaled up here. So that means that this distance is 8 as well. So an observation we believe we've made is that R prime is the shortest chord through P, and R prime seems to be 16. And so now I think it stands to reason that we could get any integer in between those two as we rotate, you know, from this smallest chord to what we think is the longest chord through P. So let's just sort of think, you know, so 6, 17, 18, 19 should be integer lengths that we could find somewhere through P. And we're not actually asked to find, you know, those locations, but I think we could reason that definitely there's going to be some angle at which will pass through, the integer lengths 17, 18, and 19. Now here's where you have to be a little bit careful because there's some symmetry going on. So what I want to show you isn't I guess this idea of suppose this is one of the chord length that's equal to 17. Observe if I put my finger on it that it is a little bit longer than R prime. But I guess what I want to call this, let's see, R, Q, R, let's call it SS prime. If we suppose that SS prime is equal to 17, then I would argue that we got to be a little careful here, because if SS prime is equal to 17, then I think there's another one equal to 17 that's the reflection of SS prime across the x-axis. So I'm going to reflect this across the x-axis and get something that looks like this. So S, I don't know, QRS, let's call it TT prime. Then TT prime, SS is, let's call it SS image, reflected across the x-axis is also 17 units in length. So in other words, every one of these ones that are in between 20 and 16, that is 17, 18, and 19, I can see an argument here that by symmetry they'll have a partner, one that's got a negative slope, one that's got a positive slope, that both pass through P. So there are, let's see, one chord of length 20, one chord of length, what was this one, 16, two chords of length 17, 18, and 19. So I believe that there are only 8 chords of integer length here passing through P based on this reasoning. So let me just summarize that. So conclusion, 8 chords of integer length exist. So let's just stand back and look at this example 2. We started the example out by throwing in, I guess, relying on an analytic approach where we decided to draw the circle on the XY axis and think about it, from a Cartesian standpoint. Maybe not necessary, but for me it's helpful in just sort of organizing my thoughts. And then we made an argument about the shortest chord that relied on the synthetic result, which the 3, 4, 5 triangle here, we're relying on Pythagoras, knowledge of Pythagoras' theorem. And then lastly, we were careful about the 3 intermediate lengths, 17, 18, and 19, to consider transformational geometry, the fact that if we consider x, the x-axis as a reflecting line, that each one of those lengths has a partner of equal length with opposite, I guess, with slope that's positive instead of negative. So kind of an interesting result here. I picked this problem because I thought it was such a nice problem for highlighting all 3 of the geometries playing a role in the construction of the solution So quite a bit going on here to find the 8 chords of integer length. I'll make sure and get a copy of that on our Moodle site as well. Okay, let's do one more, and here it is. Example 3, square ABCD is inscribed in a circle with diameter BD of length 2 units. So that length there is 2 units. Segment AB is the diameter of the half circle on top of the square. Okay, so the half circle, so segment AB. So that means this thing is a half circle on top of the square. What's the area of the shaded region in square units? Express your answer as a common fraction. That's kind of an interesting statement. They give away the fact that the area of the shaded area is actually rational, so there must not be any irrational term in that. Let's go ahead and see if we can dive into that problem. Okay, so I guess we'll start with a circle. Inside that circle, we're going to draw a square. Let's see. So how would that be easily done? I guess I'll pick that and use my compass, or excuse me, the grid lines on the paper to sort of do this. Draw a rough square. Not going to be perfect, but it'll be close. And then let's see, so we need to find the center of this. That's 2 1/4, so 1 1/8, about right there. And we're told this is a half circle centered on that diameter. And it's this region that we're after. And let's put in our labels A, this is B, this is C, and this is D. We're also told that this diagonal is of length 2, and that ABCD is a square. Okay, so this is example 3. And this is a half circle. Okay, so it seems like right away, no need to take an analytic approach or coordinatize any of this. It seems like we're going to dive in with some synthetics and maybe see what happens there. Let's see. So one thing that would be helpful is to start labeling a few things. I'm going to call this region 1. That's what we're after. We're after region 1. I'm going to call this region 2. If that's region 2, then this is equal in area to region 2. I'm arguing symmetry there, right? By the symmetry of the problem. There's a fourfold symmetry in the rotation of the figure. So it seems like each one of those we could call, I guess equal in area. This we could call region 3 and this region 3. So hopefully by doing some addition or subtraction, we can somehow figure out what region 1, the area here that's shaded, is. These things are often called loons. So region 1, the loon, region 1. So let's go ahead and see what we can get after. I think the first thing that we should probably go after is the areas of the inside figures here, region 3. We have a right triangle drawn inside a square. So the diagonal here means that this side length and this side length are the same. So we must have a 45, 45, 90 right triangle with diagonal 2. Using the synthetic result that isosceles right triangles have base angles that are congruent, and that works both ways. If base angles are congruent, then you have an isosceles right triangle. We can argue that these two sides are equal in length and then apply Pythagoras. So Pythagoras would say that the side length here, let's call it x, plus the side length x, so we'll call this x and this x, squared must equal the hypotenuse squared, which is 2. So what do we get? We get 2x squared is equal to 4. So x squared is a half, and that means that x itself is the square root of a half, or 1 over square root of 2, or if you want to rationalize this, root 2 over 2 as the length of x here. So that's root 2 over 2. So that allows us then to calculate what region 3 is. So region 3, which is this sort of triangular region here, is going to be 1/2 base times height here, so root 2 over 2 times root 2 over 2. So 2 on top and 8 on bottom. So that looks like region 3 is equal to 2/8 or 1/4 units squared. Okay. So that's what region 3 is. So that means these two together comprise an area of oh, no, I did it. I'm okay here. Oh, I see where I made my mistake. Oh, you're probably pulling your hair out watching me do this. So 4 divided by 2 is actually going to be 2 here. Okay, I'm all off. And I'm going to let this fly just so you know that I also make mistakes. And so that means that the x value is actually just root 2. Sorry about this. And we'll correct this. It seemed quite small to me when I got here. The reason I was alerted was because the diagonal here is 2, and I thought to myself, well, how could this just be 1/4 and 1/4 and a half? It seemed quite small to me. So we'll see how that changes things. Root 2, so that's 2 over 2. Well, that means that region 3 has a unit as its area, which means that we can erase that. Unit squared. So that means that the area of square ABCD has got to be equal to 2 times region 3, which is just going to be 2 units squared. And that makes sense, of course. If this is root 2, then that's root 2. So root 2 times root 2 is just going to give you 2 for the whole square. Okay, so we found this area. Now the question would be then, well, how could we find we could probably find the area of region 1 plus region 2, because that's half the area of a circle, and we know that the distance x here is root 2, so the distance, the radius here is going to be root 2 over 2. So let's do that. So let's see, the area of R1 plus R2 is going to be half the area of the circle. So half the area of the circle with the radius pi r squared, root 2 over 2 squared. I take half of it because, of course, region 1 and 2 comprise only half of a circle whose center there is in the middle between A and B, the midpoint of A and B. So let's go ahead and compute that. If I square the square root, I get 2. If I square 2, I get 4. So I get 2 on top, 4 on bottom times 2, so 2/8. 2/8 pi, or just 1/4 pi units squared. So I know that this is a 1/4 pi, and I know that this piece is 2. If I could find what region 2 is, I could subtract it away from the region 1 and region 2 to solve the problem. And of course, here's where we're gonna use subtraction again. We know what the square's area is, and we could certainly find the area of the circle. So if I take the square away from the circle, it'll give me what these 4 region 2's add together to make. So let's see. So the area of circle, I'll call it ABCD, the circle passing through A, B, C, and D, is going to be equal to pi times the radius squared. Now the radius here has got to be half of the diagonal. The diagonal is 2, so this distance has got to be 1. So 1 squared, so that's just pi units. So how would we figure out what each one of these R2s is? Well, we take the area of the circle and subtract away the area of the square. So we'd subtract 2 units away from pi units, but then we'd have to divide it by 4 to find out what one of these areas R2 are. So the area of R2 is going to be equal to 1/4 of the area of circle ABCD minus the area of square ABCD. So that's going to be 1/4 of, let's see, the area of the circle we said was pi. The area of the square we said was 2 units. So that's going to be 1/4 pi minus 2 divided by 4, or 1/2 units squared. So each one of those little R2s is equal to that amount in area. And so now I think we're able to combine these two results to find the area of just region 1. So area of region 1 is going to be what? The area of region 1 plus region 2 minus the area of region 2. So region 1 plus region 2 is 1/4 pi minus the area of region 2, which is pi over 4 minus 1/2. Interesting. So the pi over 4's cancel, and we're left with just 1/2. And so therefore the desired area R2, or R1, sorry, in the drawing, is equal to 1/2 units squared. So it's only, that's a 1/2 a unit. So kind of interesting to think about. That region right there is a 1/2 a unit. Would be equal to, we know that this, for example, is 1 unit. That region's area is equal to, I guess, half of region 3, which is 1 unit. Yeah, that's really a fascinating result. In other words, if I kind of drew in this diagonal, this triangle right here would be the same area as that loon. So let's stand back and look at it from a perspective of the 3 geometries. I don't think we went to analytic geometry at all here, but I think there's a lot of interplay between synthetic geometry as well as transformational geometry. We made lots of symmetry and rotational arguments when we said R2 was equal in area in these 4 regions. When we talked about the midpoint here being the center, as well as the midpoint here being the center, we're arguing symmetry there. And then a ton of synthetic geometry going on with quite a few applications of, well, at least one application of the Pythagorean's theorem, as well as area formulas, which sort of border on some synthetic results there. So hopefully that gives you a good sense of what I'm trying to argue here, that in true problem-solving settings, I really think it's true that what you see is an interplay between the 3 geometries. And I really think the only way that that students get good at this sort of stuff is by just doing lots and lots of geometry problems. And we as teachers would be good. One way we can help them is to give them opportunities where problems like these that come out of Math Counts require students to access tools from across the perspectives that are commonly taught in K-12 geometry. All right, well, that's really it for this week. I'll make sure that the copies of my handwork are available on the Moodle site, and I wish you luck in your content area problems for the week as we finish up.